this. Let's say I have a chemical like what I'm drawing right here. Let's make sure that we understand what this means. So what do each of these points represent?
Carbon.
Carbon. And this intersection is carbon?
Yeah.
Right? Good. How many carbons are there total? Take a moment. Don't say anything, but just take a look. Okay. So how many carbons do we all see?
8 total.
8. Does everybody agree?
Yeah.
8, and I would agree, 8. Good. How about hydrogens? Take a moment. How many hydrogens?
18?
I'm getting 18 if I do this, yeah. And if we wanted, we could fill everything in. It's kind of ugly looking, right? Let's see if I can enlarge the whole thing. There we go. Oops. Try that again. There we go. So that's one way of writing it, showing all the carbons and how many hydrogens there are. Good. Now you'll notice if you go to the functional group list, this does not match any functional group. This molecule has no functional groups, okay? Because it only has carbon-hydrogen single bonds. We call any compound that has only carbon-hydrogen single bonds, we call it an alkane, okay? So that is like the lack of a functional group is an alkane. If it's got a ring, we call it a cycloalkane. But these are still considered absence of a functional group, okay? So to speak. So please just recognize that this is not having a functional group. Any questions about that?
Hydrocarbons aren't a functional group, right?
No, yeah, they're not. They're a broad class of compound. But if I add this, now what kind of a functional group do we have? That's a carbon-carbon double bond.
Is that an alkene?
That's an alkene. Good. So now we would say this is an alkene. Or we would say this is an alkene. Okay? So if there's nothing but carbon-hydrogen single bonds, that's an alkane, and we don't call alkanes a functional group. As I said, it's like lack of a functional group, essentially. They are the most boring, so to speak, of our chemicals. They don't really tend to do a lot of reacting except burn. For the most part, that's what they're used for, is fuels. But there are certainly exceptions. Okay. So I'm going to draw some chemicals that will have more than one functional group in them. I would like you to practice drawing these. And identify the functional groups, please. I'm not going to draw lone pairs. Oops. Okay, so there's one. Another one.
Oh, interesting.
Oops. Okay, so redraw those if you haven't done so. And I want you to identify all the functional groups that you see. All right, good. So I've unpaused here. Let's go ahead and name these to see what we have. So we'll start with molecule that I've not labeled number 1. What functional groups do we have?
Carboxylic acid.
Yeah, so right here, I'll just draw it like this. Well, no, that's not very nice. You could circle it. You could just draw an arrow to it. This whole group right here is a carboxylic
Acid.
acid. Good. I mean, if you circled it, it would be this, right? So that's
Professor?
a acid. Yeah.
Are you circling something?
Yes. I'm sorry.
Yeah.
Hold on.
Yes.
I don't know if it's just, oh, thank you.
I'm gonna.
Yeah, there we are. Well, it's not exactly a circle, but you get the idea. So there's a carboxylic acid. Okay, what is that?
Thiol.
It's a thiol. And then this guy right here
Amine.
is an amine. So you can use arrows, you can use brackets, just be as clear as you can. I mean, I would even accept it if you just wrote, oops, oh, not that. If you just wrote, well, once it's there, I can't seem to get rid of it. All right. There are no other functional groups on number 1. You should not have said alcohol, okay? Because remember, OH next to a carbon-oxygen double bond is a carboxylic acid. That's different from an alcohol. Okay. How about on number 2? Going from the left, what do we have on the extreme left?
An aldehyde.
That is an aldehyde. Good. Why is it an aldehyde and not a ketone?
The hydrogen.
Yeah. Because of the hydrogen. Okay, so this whole thing is an aldehyde. What is this right here?
An alkyne.
An alkyne. What else do we have?
An ether.
Good. Yeah, so this carbon to that oxygen to that carbon, right? It's an oxygen bonded to 2 carbons, and neither of them can be double bonded to another oxygen. So this is an ether. And then down here,
Halide.
yeah, an alkyl halide. Good. Incidentally, I'm assuming most of you are going to be taking Chem 231 in the fall, right?
Yep.
Just be aware that when we throw chemicals in waste, obviously none of this goes in the drain, okay? Alkyl halides get their own special waste. These are called halogenated compounds, okay? Sodium chloride is not halogenated. That's just sodium chloride, okay? But anything with a carbon halogen bond is, we call that halogenated or an alkyl halide. Good. Questions? No? Okay, how about 3? Going from the left, we have an
Ester.
good. This is an ester. What else?
Diethylamide.
What's that?
Diethylamide.
No, that would be the name of a compound.
Oh, I was looking at the wrong amine. Sorry.
No, it's not an amide. This is an
Oh.
amine. Very important.
Oh, I meant to say the one with the N. Yeah. Yeah.
But a lot of people will accidentally say amide because they see the double bond oxygen. For it to be an amide, that double bond can't be there. It would have to be where? It would have to be right next door.
Yeah.
Okay. So an amide would mean the double bond oxygen is right next door. Just like with an ester, it has to be O, C, O, C. Good.
Mhm.
Yeah. And then what do we have at the far right?
Ketone.
Yeah, this is a ketone. Good. Okay. What else do we have? How about on 4? What is this right here? This might be tricky at first.
Ester.
This right here, almost, not an ester.
Ether.
Ether. An ether can be in a ring like that. That's totally fine.
As long as it's a bridge.
Yeah.
Between the two.
This has to be a bridge between two carbons. The chlorine, we call this an alkyl halide again, right?
Mhm.
And one more or two more. We'll see what's left.
Ketone.
Good. Is this a carboxylic acid?
No.
No. A lot of people will incorrectly say yes, but the difference is, remember, carboxylic acid, the OH has to be right on the carbon-oxygen double bond, right? Here it's not. It's on a CH2, and that's bonded there. So this is another ketone. And then this is an
Alcohol.
alcohol. Okay. The compounds can get much more complicated than this. For example, let's consider polytoxin. Polytoxin is the single most poisonous substance known, not found, which is not a protein. Okay, like snake venoms are usually proteins. What do we see here in terms of functional groups? What are there lots of in polytoxin?
Alcohol.
OH.
Lots of alcohols, right? Lots of alcohols. Lots of carbon-carbon double bonds, which are alkenes, right? Lots of ethers, like there's an ether, there's an amide. So, they can have many, many, many functional groups here. Okay, so that is very, very much possible. Okay. We can thank bacteria for creating these very, very deadly compounds inside other things. And most of the time they are marine organisms. In this case, I believe it's a type of seaweed, okay, which is that deadly. So don't just go randomly eating seaweed. All right, so any questions about this? No? So we will resume with the rest of chapter 2. Oops, I seem to have turned off chapter 2. There we are. Okay, so that got us through all of our functional groups. So it's very important that we understand all of those guys. Okay. Now, we already talked about how to do formal charge. So it's very important that you be able to identify formal charges in molecules rather rapidly. So for example, here is a chemical, and I would like us to identify the formal charges based on everything that we see there. So that's right here. I didn't get rid of that question, did I? I'm sorry. Unfortunately, all these labels got doubled, but I'm hoping everybody can still understand them. Some of these groups don't look like anything you've seen before, and that's totally okay. Okay, so if you notice, none of the carbons have formal charges here, and neither do the hydrogens, of course. So let's just go look at these atoms one by one. So this oxygen. Oxygen has a valence of what? 6. Good. It's making 3 bonds, and has 2 lone pair electrons, right? So 2 plus 3 would be 5. So what is the charge here?
+1.
+1. Good. So we can either write plus or plus with a circle. The oxygen, valence of 6. It's got 2 bonds and 4 lone pair electrons. So that would be a charge of
2.
0. 0. Okay? Because remember, oxygen's valence is 6. So 6 minus 4 minus 2 would be 0. Remember, 1 for each bond and 1 for each electron. Sulfur is in group 6A, so it has a valence of 6. So what is its formal charge here? It would be 6 minus the number of bonds would be 4 minus 2 for the 2 electrons. So its formal charge is
0.
0. So we don't need to write anything, okay? The nitrogen, what is the valence of nitrogen?
5.
5. So it's making 3 bonds and has 2 lone pair electrons. So 5 minus 3 minus 2, it would be 0.
0.
Good. This oxygen, valence of 6. It's got 6 electrons and 1 bond. So its formal charge would be
-1.
-1. Good. You can put, I usually like to put it on the right, but you see you can put it on the left, so long as it's close. And then finally, that last nitrogen. Nitrogen, as we said, has a valence of 5. It is making 4 bonds and has no lone pairs. So 5 minus 4 would be
+1.
+1. Good. +1. It is very unusual to see anything other than +1 or -1 in organic chemistry. There'll be some times where we might see sulfur with -2, but not often. Okay. What if carbon has a charge? This will be a very important thing to study because these tend to be extremely reactive, very, very reactive, very unstable. So most carbon atoms, 4 covalent bonds, no formal charge. Sometimes we will find carbon with a +1 charge. And the only way we'll generally run into it with a +1 charge is if it's making 3 bonds, and that's it. That's really the only way that could happen. So, for example, if you see this molecule here, the carbon is making 3 bonds. The only way it could be positive is if it's missing what? What does it not have? It does not have a hydrogen. Okay. And it's usually confusing to use bond line structures when carbon has a charge. I commonly recommend not doing it and just filling in the label. So if it were me, I would usually write a C there. I'd draw these others out and put a plus, because that way it's very clear there's no hydrogen. If I see this symbol, I say, oh, carbon must be making 3 bonds. So there's 1, 2, and the missing bond is hydrogen. So I would usually draw in the hydrogen. So even though that's how the book is doing it, I would recommend doing it like this, usually. Remember, you are allowed to show hydrogens if it makes things less ambiguous. Okay. And again, if you circle it or you don't circle it, it doesn't make a difference. I think people circle it so they don't think it's an X or something else. Other than that, that's fine. And finally, this last one. If this has a plus, that means we only see 1 bond. If it's plus, it needs 3 bonds. So there'd be 2 hydrogens there. So I would usually write that again more like this. Because it's less confusing. If you draw in those 2 hydrogens. And usually I would draw in the C, but you don't have to. But the goal is you just never want it to be confusing. So that makes it explicitly clear that this carbon has 3 bonds. 1 of them is to carbon and 2 of them are to hydrogens. That term is extremely important. Those are called carbocations. Okay. So nitrogen is a cation, this oxygen is a cation. When it's a carbon, we will use the word carbocation. Carbocations are, in the vast majority of cases, quite unstable. What is it about them that makes them unstable?
They don't have an octet.
Yeah, exactly. So the reason is yes, okay. In addition to having a +1 formal charge. So charges make things less stable, not having an octet. Okay. Sometimes carbon will have a -1 charge. And these are called carbanions. And if it has a -1 charge, that would mean what? It's generally making 3 bonds and has a lone pair. Carbanions are also unstable, although they have an octet because they have a negative charge. This guy is extremely basic. If this were to hit water, it would basically burst into flames. Okay. If there were 3 CH3 groups right here, it would be even worse. If you had a syringe of that and you shot it out of a syringe, it would catch fire the instant it came into contact with water in the air. Okay, so violently reactive. That's because it's usually dissolved in a very flammable solvent, so it would instantly ignite the solvent. Okay, so those are carbanions, and these are carbocations. You do not need to know about them at this point, and probably not at all. But there is another type of species which is very strange, like this one. So don't worry about it right now, but I do want you to, but I could ask you what the formal charge is. Be very careful on this one because a lot of people will get this wrong. I'm sorry. Let me take that away. There we go. One lone pair, one lone pair. This thing is very, very rare. We almost never see this. What is the formal charge? Let's be very careful. Carbon is making 4 bonds. So minus 2 electrons, minus 2 bonds. It is 0 charge, right? 0 charge. But it is outrageously unstable because it has no octet, right? It doesn't have an octet. These are called carbines. It is a carbene. In one of the labs we talk about later on that we would normally do, we use dichlorocarbene, which would be Cl and Cl. They are used for making triple bonds because it's so violently reactive, it will attack a double bond carbon and attach itself to make, basically it'll make a 3-membered ring. So anyway, 0 charge. Don't worry about carbines. You won't be tested on them unless I ask you what's the formal charge. And the only reason I would ask you that is to test you to make sure you know how to do the calculation. Carbon has a valence of 4. So 4 minus 2 electrons, minus 2 bonds, 0 formal charge. Okay. Formal charges must always be shown. Lone pairs on carbons must always be shown. Okay. Because again, they are so rare, so unusual. You can get away sometimes with leaving them off of oxygen and nitrogen when they're neutral. But I generally recommend showing them if there's any possible confusion that anyone could have. Okay, so the goal is represent it in a way that there's no confusion. Okay. Sometimes lone pairs are omitted. And like, for example, this would be a bad example. You don't want to do this and leave the lone pairs off because this isn't a structure that we've talked about yet, okay? If you do this, it's kind of it's very ambiguous what you mean. Do you mean this? Do you mean this? Or even worse, this with 1 electron off on its own. It's called a radical, okay? So I know it's saying, so again, if you draw formal charges, you could figure it out. If you leave out the lone pairs, but you knew the charge, you could figure it out, right? Like you could figure out that this has to have 2 lone pairs if you wrote a minus here. If you wrote a plus here, you'd be able to figure out that it must have a lone pair. You'd probably never figure this out. So again, the rule is whenever there's ambiguity, not only must you show the formal charges, you should show lone pairs if there's any chance someone's going to be confused. Not anyone, if I would be confused, let's say. If there's any chance I could misunderstand, make sure you draw them. Okay, so as I said, if you know the formal charge, you can always figure out how many lone pairs are present. Because again, we have the calculation. It is the valence minus the number of bonds minus the lone pair electrons. So if you saw a minus here, on this nitrogen, you saw a minus. That means 6 would be the number of electrons you have, right? So the only way you'd get to 6 is 5 minus 2 minus what? 5 minus 2 minus to -1 would be minus 4. You'd need 4 electrons here. That's the only way that could happen. But as I said, I don't usually, even though this is the way the book teaches it, I say draw the lone pairs if there's ever ambiguity. Okay. Here's an example where people often do leave out the lone pairs because this kind of structure is so common in organic chemistry. We see it so often. We should just see the lone pairs in our head. So if we look at that one, if it's negative, that means what? So that would be 6 minus 1 bond minus X equals -1. 6 is the valence of oxygen. 1 for the number of 1 for the bond. -1 for the charge. So what does X have to equal?
6.
X equals 6, which means I have
3 lone pairs.
3 lone pairs, right? Good. That would be the pattern. That's about the only time you'll see a negative charge without showing the lone pairs. And even then, I don't ever do that. I always show the lone pairs. Okay. So it should have 6. 3 lone pairs, which would be 6 electrons. Or you just have to know the pattern. And that's usually what I recommend. You just need to know the patterns. So for oxygen, these are the important patterns. Neutral oxygen has 2 bonds plus 2 lone pairs. Negative oxygen has 1 bond and 3 lone pairs. And positively charged oxygen has 3 bonds and 1 lone pair. Okay. Any questions about that? Again, it's just seeing the pattern. For nitrogen, it's the same thing. You just want to see the pattern. We know that nitrogen generally has 3 bonds and 1 lone pair. Whenever you replace a bond with a lone pair, it's going to become more negative. We saw that here, right? If you replace a bond with a lone pair, so 1 bond, 3 lone pairs, it's negative. And whenever you replace a lone pair with a bond, it becomes more positive. So this pattern is fairly common. This is very common. Nitrogen making 4 bonds with a +1 charge. So you agree you don't want, after a while, you shouldn't have to be doing the formal charge calculation. That's the goal. After a while, you should just see it. Nitrogen 4 bonds, no electrons, +1. Just makes it easier. So any questions about that then? I would recommend on sulfur doing it the old-fashioned way. For example, people will often make a mistake on this compound. This is a very important solvent called DMSO. It is almost always written like this. And almost everybody looks at that and says, oh, it's done. That's it. Everything looks fine. And if I ask you for the shape of the sulfur, you would probably say trigonal planar. And you would be wrong. Because if there's no formal charge on sulfur, right, there's no charge here. If there's no formal charge on sulfur, what's the valence of sulfur?
6.
6 minus 4 bonds. See, that doesn't work because then you'd have a +2 charge, right?
Mhm.
So even though everybody leaves it out, what is there that you're not seeing?
A lone pair.
There's a lone pair.
Mhm.
And everybody leaves it out, and it's very annoying, not students, but all the books. So like for whatever reason, no one draws it in. But it's there because that's the only way this could be 0 formal charge, right? And sulfur can exceed the octet rule, so that's why it's there. So this would have to be there. So now what is the shape? Sulfur is bonding to 3 atoms and has a
Trigonal
lone pair.
pyramidal.
Trigonal pyramid, yeah, it's a trigonal pyramidal. Good. Okay, not trigonal planar. So sulfur, you can get tricked a lot. Phosphorus, the same thing sometimes. So, but never oxygen and nitrogen. They're always going to be nice, honest friends. They will always follow these patterns. Same with carbon. We will never, almost never, see halogens with charges. The only time we will see that is in a very unstable complex we see next semester. And I'll call attention to that when we see it. But it's very unusual. Actually, no, we will see it this semester. But it's very unstable, and it's only used as what we call a trans. It's only used as an intermediate. Okay, so molecules. Most of them are 3-dimensional. This is why I've said you need to buy model kits. All right, you need model kits to understand them 3-dimensionally, especially once we get to chapter 4. Okay, so it's important that you understand that when we draw a bond as a straight line, we usually mean it is in the plane of the paper. Okay, it is in the plane of the paper. A wedge is when this is drawn out like a thick triangle. The way this is drawn indicates the chlorine is coming out at you. Does that make sense, so to speak? The chlorine here is coming out at you. On the other hand, dashed wedges like this means they're going away from you. So as I look at this on the screen, this chlorine is coming out of the screen towards me. And this chlorine is behind the screen, is the way I should be seeing this. Okay. Now remember, of course, these molecules can always flip upside down. If I flipped it upside down, what would happen? The chlorine that was coming out at me would now be going away from me. And the one that was coming away from me is now towards me. Okay. This is one where we have a ring. This OH, this alcohol, is going away from you. This alcohol is coming towards you. And then this kind of weird little structure is bicyclic. Bicyclic means 2 rings. It's technically 3, but we call it 2. So we have a 6-membered ring here. What is this thing right here? What must that be? There's an atom there.
A carbon?
That's a carbon because it's where 2 lines are meeting, right? So that carbon is out of the screen. It's in front of the screen is what it's understood as being. It's coming out at me. All right. The bromine is also coming out at me. And this carbon right here, remember, if there's nothing at the end of it, it must be a CH3. It has to be a carbon. It's going away. Please never do this. I hate this. Never make up your own symbols. Okay? Please never do this. That doesn't mean anything to me. It must be like this. Okay? I look at this and I go, was that just a way of drawing it like this? that you just didn't fill it in. You just didn't fill it in. I don't understand what that means. Okay. So never draw that without filling it in. And if you do fill it in, that means it's coming away from you. Okay. Dashes can look like this. These are the best kind, or they can just be straight lines, all the same length. Some people will also draw them as dashed lines, but I don't recommend it. I like to use dashed lines for hydrogen bonds, and that's usually what we use them for. Although it would be clear from the context that that's not hydrogen bonds. Okay. So please stick to the way that you're seeing them here. Okay, so chapter 5 is where we will really start getting into this. We will deal with it somewhat in chapter 4, but chapter 5 is where we really start looking at this. This is stereochemistry. There are other ways of drawing structures. Okay, and we will explain what all of these mean as we come to them later on. Some of them should be kind of obvious, others not. This is called a Fisher projection. We'll talk about it in chapter 5. How many carbons are there if you were to look at this based on what you think you would know, what you would normally know?
Five.
And that's correct. There are 5. So each cross is a carbon, right? So there's a carbon here, a carbon, a carbon, a carbon, and then where it says C, obviously that's a carbon. So there should be 5. This is showing a ring, but you're looking at it as if you were in the paper looking at it straight. Okay? So imagine that you took a ring and it's flat and you just turned it so that you're looking straight at it. That's called a Haworth projection. That's very important for carbohydrates, which we'll see a lot in towards the end of the class. And then this is a bicyclic compound. So this structure right here is the same as this kind of a structure. So here you are looking at it from the top. And here you are looking at it from the side. It should kind of make sense that this is called a bridgehead carbon. It is a bridge from one carbon to the other across the ring. Does that make sense? If this was a lake, you would need a bridge. So it's a bridge carbon. We'll talk about these more in chapter 4. Okay. Now into what is by far, well, all of this is important. Anything in the notes is important. But what is probably the single most important concept that we will deal with conceptually for understanding answers. In this class, I will often ask you, explain why this is the case. And it's not a coincidence. 90% of the time, well, 80% of the time, the answer is this word, resonance. You have to understand it. So you can't just say, you know, if I ask you, well, why is this resonance? Okay, but why? You have to understand resonance. We talked about resonance in Chem 130. What is resonance? What does it mean if we say 2 molecules have resonance structures? If 2 molecules have resonance structures, that means, does anyone remember? It's a hard concept, but essential. Resonance structures is when you have molecules with the same connection of atoms, but different placement of electrons. Okay. So this is the allyl carbocation. I want to show a resonance structure of it. First of all, this does not totally represent the full structure. Let me draw in the hydrogens. I don't like that plus being there. draw the hydrogen there. I like this better. Good. Okay. So how many carbon atoms do we see here? 3. So this is one way to represent this molecule, but it is not the only way. The other way of representing it would be like this. And let me put those hydrogens in over here too. Look very carefully. What has not moved? What has not changed at all between these two?
The carbons,
Good. And what else?
the hydrogens,
Good. And there's a hydrogen here too, right? If we wanted to draw it in. So in other words, if the carbons haven't moved and the hydrogens haven't moved, what haven't moved? None of the atoms have moved. That's the importance. Specifically, the nucleuses of the atoms. The atoms have not moved. What is the only thing that's different between these two? What have moved?
The electrons.
Only the electrons. And technically, if the electrons have moved, that means it looks like the charge has also moved, right? Because if the electrons are over here, this carbon has the plus charge. If I draw the electrons over here, this side has the plus charge. So that means these have the same connections of atoms. Everything is the same in space. Only the electrons have moved. Okay? What we are saying here is these electrons are a very important word. They are delocalized. Localized means stuck in one place. But these two electrons in this pi bond are delocalized. They can be here between these two carbons, or they could be here between these two carbons. We could also say the positive charge is delocalized, right? Because I could draw it on this carbon or on this carbon. The first thing I want to be very clear about, neither of these are real. And I've seen this, for example, on old MCAT exams, if you apply for med school. Neither of these is real. The real answer, the real way to describe it is it's a combination of both. Okay? So these structures help us to understand these compounds, but neither one of them is real. Okay? The real structure has all 2 electrons localized all over. They are moving across the whole thing. This is why we did MO theory, molecular orbitals. The electrons are being moved all across this space. Okay? So that would be called a hybrid, as we will see. It is both of them together. Okay. What is the hybridization of every carbon here? This carbon is easy to see.
SP3,
No?
SP2,
sp2? Good. What is it when it's got a positive charge? Is it still sp2? How many bonds is it making, the carbon?
3.
3, so it's still sp2. Good. This carbon is sp2. This carbon is sp2. These 3 are all sp2. This is a very common thing when we have sp or sp2. We don't usually see resonance nearly as often with sp3 unless there are lone pairs. Okay. So If these are sp2, then what other orbital is there that we're not showing in the picture? sp2, sp2, sp2. How many p orbitals are there on a carbon atom? 3. We've used 2 of them, right? sp2. So there's a p orbital left over here. And that p orbital acts as the conduit. All the electrons can flow through those p orbitals. This is what it's trying to show here. sp2, sp2, sp2. All 3 p orbitals are parallel to each other, so that means the electrons can be delocalized. They aren't stuck between this carbon pair or this carbon pair. They are smeared out over all 3. Okay. And because the electrons can be distributed all over, we call that resonance. What it means is it's like it's resonating between all of the different structures. If we looked at them as MOs, these are the way the MOs would look. And we will learn how to draw these for certain compounds, especially the one that we're looking at right now. There is a bonding molecular orbital, a non-bonding, and an anti-bonding. We haven't talked about non-bondings yet. But look at the bonding one. This is very important. The bonding one looks like what? It looks like we took all of these and we, instead of having a pi bond or a pi bond, we made one long pi bond, right? Does that make sense? One long pi bond across the top and the bottom. Non-bonding has a node right at that carbon, and anti-bonding has 2 nodes right there. Now, very important to understand is how many electrons are there in each of the MOs for the allyl carbocation. The way that we do this is we look at how many pi electrons are there, plus how many lone pair electrons are there. So how many pi electrons are there? Electrons in the pi bond? A bond has how many electrons?
2.
2, good. So there's 2 electrons here, and this p orbital is empty. So there's a total of 2 electrons. 2 electrons. Where are they? Bonding, non-bonding, or anti-bonding? Remember, you always fill lowest energy first. So where are those 2 electrons? They are in the bonding molecular orbital. That's just telling you those 2 electrons are being spread out all across the molecule. Do you think that's going to make it more or less stable? This is very, very important. Being able to delocalize always makes something more stable. So resonance will be vitally important for understanding stability. Okay. So how do we show the complete picture? As I already showed you, there's 2 ways. These are 2. What do you notice about the 2 structures compared to each other? They're the same, except flipped over, right? Whenever you get something like this where they're the same but just flipped over, we call them equivalent, okay? That does not mean there's 1 resonance structure. There are 2. We pretend that this is carbon number 1, 2, 2, 3. For the time being, we see them as being different. But you do agree if you flipped this around, it would look exactly like this picture. And that means that makes them especially stable when you get 2 equivalent ones or 3 equivalent ones. Okay. Now, that's not to say this is stable. This is still very reactive. It's just more stable than if it didn't have resonance, as we will see. Okay. So remember, this is not the correct way of drawing it, nor is this the correct way of drawing it in reality. It's just the way we do it on paper. But the reality looks more like this, where the dashed line is showing you what? That the electrons are
Spread across.
Yeah, they're spread across. The 2 positive partial charges tell you what also? That the positives can be on either side. Okay. We use this arrow here to indicate resonance. Very important that you know that. There's going to be tons of different kinds of arrows in this class. Well, like 6 or 7. This is one of them. This arrow always means resonance, and we don't use it for anything else. Okay. It is different from equilibrium because at equilibrium, what happens in equilibrium? Equilibrium means sometimes you have this molecule, sometimes you have this, but they're final structures. Those are basically stable molecules. Like, for example, if I said we have an equilibrium, let's do a simple equilibrium case. Or I could write it like this. Remember, there'll be an equilibrium constant here, right? Because that's an acid. Does HF exist? Here, let's start with the easiest. Does water exist?
Yes.
Yes. Does HF exist?
Yes.
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 Hydronium?
Yes.
Yes. Fluoride? Yes. These all exist. Okay. So in equilibrium, all this is telling you is how much you have of one side compared to the other. With resonance, remember we said that neither of these really exist. They're just ways of representing the two important ways of representing what this molecule really looks like, more or less. Okay. It's kind of half like this and half like this, but they don't really exist. The only thing that exists in reality is something that looks more like this, which is to say that there's a positive charge on either end and there's electrons being shared across here. There's no way to draw it perfectly because it's a picture, it's a combination of two pictures. So the word we use is that this is a hybrid, a resonance hybrid. Okay. We try to come up with weird analogies. Like we say, a nectarine, this is what the book suggests. A nectarine is a hybrid by mixing a peach and a plum. A nectarine is not a peach sometimes, and it's not a plum sometimes. Okay? A nectarine is always a nectarine. Just like a mule is not a donkey, a mule is not a horse, a mule is a hybrid between a donkey and a horse. Or like a labradoodle, right? A labradoodle is not a Labrador or a poodle, it's a hybrid. But I don't like that because Labradors do exist and poodles do exist, so it's not a perfect analogy. Okay. Okay. So resonance always makes a molecule more stable. So whenever we can delocalize electrons like this, it means that the electrons can be spread out over greater volumes, over greater numbers of orbitals. That means there's less repulsion at one spot or another, or less attraction. So I would not say this side is the only positive side and this is the only positive side. It's the formal charge. Formal charges are generally unstable. This spreads it out, spreads out the formal charge. Okay. And so ultimately, it's better to have electrons over many nuclei than just one in general. Okay, so now we're going to focus on the thing that's the most tough, but it's critical. After the first exam, we're going to get into things called mechanisms, and they will usually be about 25% of every exam. So this is the first chapter that you have to really master in order to understand mechanisms when we get through there. The curved arrow. We must understand how curved arrows work. Curved arrows are used to represent movements of electrons. Okay. A regular arrow means movement of electron pairs. A fishhook means movement of a single electron. For right now, we're only going to focus on this side. We will deal with movement of a single electron later when we get to talking about radicals. Okay, so that's quite a ways off still. The side of the arrow without the barb is where the electrons start. The arrow points towards their destination. Does that make sense? Arrows usually point towards destinations. So an example, yeah, it's a bad example. Let me do that again. No, that's really bad. Okay, so we've said that there's a positive charge here, right? And we have pi electrons here. I can draw an arrow as so. And the arrow is pointing between the two atoms over here, right? What that is telling me is that I should take the electrons, those two electrons, and move them from being between these two carbons to being between these two carbons. Remember, the only thing that is allowed to move is electrons. I did not move any atoms in a resonance structure. And remember, the positive charge just happens to move because the formal charge is changed when that happens. The atoms themselves did not move. So that is an example of a curved arrow. It is showing these two electrons moved from here to here. We need to understand how this is going to work. The first and most fundamental idea is negative likes positive, which means electrons are usually going to move towards an area that's more positively charged. Does that make sense? In a structure. They don't want to be stuck. They don't want to ever go towards something else that's negative. Okay. We will show curved arrows in reactions later, but right now we're just showing them for resonance. So here, this is showing an electron moving up here. So what will you end up with at the end? The lone pair will know these electrons will not be here anymore. They will be a double bond right there. Okay. Rules. Rule number 1. Never break up a sigma bond or a single bond. Never, 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 never. Why is that forbidden? If you move a single bond, these atoms are no longer attached, right? And you no longer have the same connection of atoms. You can move double bond electrons and you can move triple bond electrons. So in other words, pi bond electrons. But you may never move electrons in a single bond in resonance. You can do it in reactions, but not in resonance. And we're only worrying about resonance right now. Okay. So resonance then is when there's overlapping p orbitals, for example. So sp, sp2, okay? sp3 only when they are lone pairs, as we're going to see, or where there's a place to take them. Rule 2. This goes without saying. You never exceed the octet rule for any elements in the second row of the periodic table. Boron, carbon, nitrogen, oxygen, fluorine. This is why you must keep very, very careful track of hydrogen atoms so that you do not exceed the octet rule. The biggest sin in organic chemistry is carbon with 5 bonds. Okay? Don't do it. Never, 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 never. Can it ever happen? Turns out in a solution of superacid, yes. You don't even know what superacid is yet. So, and you won't know unless you go look it up. Okay? Antimony, fluoride, something or other. But we're never going to deal with antimony in this compound, so in this class, so don't worry about it. But never, never in anything we will deal with will you see carbon exceeding the octet rule. Okay, so these are all very bad. They would make me very sad to see them. Okay, this in particular is bad because what is it showing? These lone pairs are becoming what? It's going towards a bond. So what will be the result? They're going from a lone pair to a what?
A triple bond?
To a double bond, because
Oh.
there's only a single bond there right now, right? So this means they're going from being a lone pair to a double bond. Why can't that happen?
Exceeds the octet rule.
Yeah, because that would exceed the octet rule. That would leave you with 5 bonds on carbon, correct? You can't do that. So that's a bad arrow. Same idea here, because this would leave nitrogen with 4 bonds in a lone pair. So that would exceed the octet rule. Same thing here. So in other words, they're never going to go at atoms that already have an octet, that are sp, that don't have other atoms that can be pushed away or other electrons that can be pushed away. This arrow looks fine until you do what? What do you need to do? It might look fine at first, but what's the problem with it? You have to remember the hydrogens. Don't forget the hydrogens. So how many hydrogens are on this carbon right there?
2.
2. So that carbon has an octet. So if you did that, this would be super bad. Okay, so this is not good. Okay. Your eyes should sting when you see this. Oh, God, that's terrible. Terrible, terrible. Okay. No 5 bonds. Although second row elements would like to have an octet, it is sometimes possible that they don't. So this is technically acceptable because where are the electrons moving? They are moving towards oxygen. Are you violating the octet rule? Excuse me, are you exceeding the octet rule? This oxygen has an octet, and afterwards it still has an octet. You're not exceeding the octet rule, but it's less than an octet, okay? These two are technically resonance structures. They are both valid, but what we will learn is they are not equally important, okay? The structure at the left is much more important than the structure at the right to understand its reactivity to an extent. Okay. So what will the resonance hybrid look like? If that's valid, we draw all the sigma bonds in. We could say, I'll just redraw that as a dash. And then this side is what? Partially positive or partially negative? Sometimes it's neutral, sometimes it's negative, right? And the bottom side is zero charge here, positive here. So we could draw this as positive. As for the lone of pair electrons, that's confusing. My temptation is to draw two because they always have at least two, but I don't think there's a hard and fast rule about this. And sometimes it has three, but you agree they always have at least two lone pairs. And sometimes those electrons are here and sometimes they're there, so they can move around. Okay. Redraw the structure shown. Why did I say that? Okay. I think this is what I wanted you to redraw. Okay. So when using curved arrows to show resonance, what you see is the structures will often have a formal charge, and that formal charge can typically migrate. So let's take a look at this right here. So I wanted you to draw that molecule. To make it easy, let me just well, no, I'll leave it like that. Okay. Okay, so I'm showing these electrons moving here. Let's draw in hydrogens because it's useful. If you're ever going to draw an arrow towards a carbon, it's always a good idea to draw in any hydrogens. Okay, you agree there has to be a hydrogen there so that carbon is making 4 bonds, correct? Good.
Yes.
So that way we're not going to lose track of that hydrogen. So the structure shown looked like this. And it also showed these electrons coming here. Now, the arrow at the top initially looks bad because this carbon is got an octet, right? But since this one does have an octet, but this arrow is telling us we're going to move electrons away. So that's going to be acceptable. All right, so what is this going to give me? So let's start from the top. So this arrow is telling me the lone pair is becoming a pi bond. Does that make sense? That's what this arrow is saying. The electrons are going from a lone pair to a pi bond. These two electrons didn't do anything. what's happening according to the other arrow? These electrons are going from being shared to being where? Only on the carbon. Good. So they went from being shared to belonging totally to the carbon. That is valid because nothing is violating the octet rule, right? We haven't violated the octet rule anywhere, but this is not done. If you left it like this, you would lose points. What else do you still need to do? You must show formal charges. So if everything was neutral here, oh, and this is also important, the total charge here is 0, so the total charge here must be 0. If this was -1, this would be -1. The charge, total charge always stays the same. All right, so this oxygen was neutral, but now what is it?
+1.
+1. And if there's a +1 in there, there's somewhere has to be a
-1.
a -1. Yeah. So where is the -1 now? It's on the carbon. This is called a what now? A carbanion. A carbanion. Okay. So I'll draw it down there, okay, where it's out of the way. And we usually draw brackets around your resonance structures at the end. Okay. So this was allowed because everything has an octet here, doesn't it? Or worst comes to worst, it might have less than an octet, but it cannot exceed an octet. Okay. What would it look like in the reverse direction? Let's do this in a different color. If it was in the reverse direction, so in other words, I want to get back to what I started with, the pi electrons need to go back to the oxygen, right? And what else needs to happen?
You get back the other electrons.
Yeah, those electrons go back to being a pi bond. Good. Some other things that are very bad. This makes no sense. Where must arrows always start?
Carbon?
No?
Electrons.
Electrons. So this makes no sense. Atoms don't, they never start in an atom. They can end at an atom. And by the way, this makes absolutely no sense because what does this mean? A hydrogen wants to go attack this hydrogen? That makes no sense at all. Okay, it's ridiculous. But you could have something like, you know, this. This is not resonance, though. Sorry, I shouldn't bring this up, but this is not resonance. But that is a valid arrow, because why? The electrons are going from, the arrow is showing electrons moving from here to an atom that's positive. That would be perfectly valid, but that's not resonance, okay? So I couldn't use a resonance arrow. That's a regular reaction. A reaction we would talk about later. And again, why is it not resonance? What did I just do?
Because you moved the electrons, or, I mean, you
Yes.
moved the atoms?
Yes, I created a new connection that wasn't there before, right? So these atoms are connected now. That would be a type of reaction we would study later. So I want to make a sense that, again, this is not resonance, but the arrow makes sense because it's going from electrons towards an atom. So electrons can go towards atoms, electrons can go towards bonds, but the key thing is, again, an electron would never start on an atom. That makes no sense right there, okay? Electrons must start on arrows must start on electrons, okay? So please be very, very careful about that.